slide?
Yeah, mate. Yep.
Okay. All right. Hello, everybody, and welcome to the Optimising Pulley Lagging Performance series of webinars. This is a 5-part set of courses that are run at monthly intervals, 2 separate time zones for each course. In today's course, we'll be looking at why pulley lagging is used and the consequences of failure when it does fail, and then we'll also go into some detail on the different modes of failure and what we call the 4 pillars of lagging performance. The subsequent courses, the course next month is on the engineering that goes behind pulley lagging, and we'll be looking at things like friction, shear forces, lagging design. The third webinar, we'll look in detail at pulley lagging bonding systems, so specifically cold bonded systems, hot vulcanized lagging, and direct bond. The fourth webinar, we will focus on identifying potential for performance improvement, and when we do that particular course, we'll be looking at the overall performance improvement of both the lagging and the conveyor belt. And the last webinar, we'll look at specifying pulley lagging and what are the important things to cover. So,
oh, sorry, Dave, could I just mention something?
Absolutely.
Could you just maybe speak a little bit slower?
I can.
It's just that we've got a lot of people from Thailand and a few from Laos on board, so maybe English is going to be not their first language.
No problems. It's actually interesting, Peter, because we haven't got it for this webinar, but we have just trialed a translating system. So the next webinars we will be able to make available in different languages. So people will have a little button at the bottom and they'll be able to select their own language. We've tested it out and the translation's pretty good. So if they want to attend the next couple of webinars, we just need to work out which languages to provide. I should have mentioned, if you have any questions, the webinar will go for about 30 minutes. If you have any questions, you can pop them in the chat at the bottom of the screen, and when we finish the webinar, we'll go through them. Now, can I ask for anybody to comment on why you think pulley lagging is used? So why don't we just have conveyors running with steel pulleys, no lagging?
Wear and grip.
Wear and grip. Yep. Thanks, Dylan. Anything else that anybody can think of?
Also probably corrosion to an extent.
Protecting the pulley shell corrosion. Yep. Any others? Okay. So Dylan's covered a number of them. So wear and grip, or transmit power. Grip is improved friction between the belt and the pulley lagging. Protect the shell, which Dylan mentioned. An important function of lagging as well is to actually protect the conveyor belt and the belt splices. It also is there to reduce wear on the belt cover and the pulley, and it's to prevent build-up from carryback on the pulleys, and also to help aid belt tracking. The interaction between pulley lagging and the conveyor belt is very important, and it's a critical part of optimizing the service life of both the belt and the lagging. What I want to do now is look at some ways that pulley lagging fails, and I'm going to start off with catastrophic failures. So by catastrophic failures, what we mean is the failure of the lagging is such that it requires an unplanned shutdown of the conveyor for some repair work. This is the worst type of lagging failure because it's very, very costly because it directly impacts production. If you look at these three photos, they're all catastrophic failures. The one on the left and the one in the center are debonding of the lagging from the pulley shell. In both cases, it was cold bond lagging. The photo on the right is an interesting one because although the lagging has bonded, this is actually a high tension bend pulley with hot vulcanized lagging, and the lagging's been destroyed because of the wear on the belt cover. And we'll go into the details a little bit later on as to why that happens. The next catastrophic failure is ceramic tile loss, which can be a common problem with ceramic lagging. This type of failure is obviously bad for the lagging, but it can also be very bad for the belt cover because the missing tiles create uneven shear stresses and they can cause localized wear of the belt. There are a number of reasons that tiles come out of lagging. The most common one is what we call tile loss due to debonding. So the chemical system that is used to bond the ceramic tiles to the rubber breaks down and fails. It's very easy to identify because when the bonding system fails, what you end up with is a neat little pocket where the tile was with smooth sides. So if you can see here, these little pockets. Whenever you see smooth surfaced rubber and a defined pocket, that is because the bonding system has failed. This is a lagging quality fault. It's basically it's a manufacturing fault, and it is completely preventable. The next cause of tile loss is what we term physical damage. This is where the tiles have been torn out of the lagging, and it's evident because the pocket where the tile was is rough and jagged. You can see here where the tile was. It's not a smooth pocket, it's a rough pocket. If you were able to find these tiles, you'd probably find them covered with rubber. This photo in the center is a high tension bend pulley, and again, the tiles have been torn out of the rubber backing. The next cause of tile loss is excessive heat. Excessive heat, basically, you can tell that it's excessive heat. If you look at this pulley, you can see that right across the surface of the pulley, pretty much all of the tiles are missing. What happens when you get excessive heat, and I'm talking about temperatures above 150 degrees centigrade? Basically, the bonding system deteriorates, and as a result, the tiles come out. So the way you can tell if the lagging has been affected by excessive heat is measuring the hardness of the rubber. Normally, rubber hardness is 65 to 65 plus or minus 5. When the rubber's been exposed to high heat, it can be as high as 85. Also, the surface of the rubber is severely cracked and graded. You can see here the cracking, and also the surface looks sort of glazed. And then basically all the tiles are missing. So that's excessive heat. Can anybody think of why you would get excessive heat on a conveyor or on a pulley?
The pulley's jammed and the belt's running over it, braiding it, creating heat. Would that be correct?
Yeah, that the more the other way around, James. But you're on the right track. It's more the belt jams and the pulley keeps turning.
Correct.
Yeah. So and that photo there is actually an example of that situation. The other thing that can cause excessive heat is hot materials being carried, like bitumen, iron briquettes, that sort of thing. Next catastrophic failure is what we call fatigue. This is where the shear forces, the torque that's being, the amount of power that's being put through the pulley is greater than the fatigue life of the lagging. You can see this pulley on the right. This is a drive pulley on the, I think it's the highest powered conveyor in Australia. It's got 2.5 megawatt drives, and you can see that the diamonds have been severely worn. If you look at these close up, I'll show you a photo later on, but they look like they've melted. And the photo on the left, again, this is fatigue, where the rubber has just been degraded. And the photo in the center is what you get under the pulley when that's happened. All of this black dust has actually come from the pulley lagging, and some of it from the belt. On high powered drives, this is where you are most likely to see fatigue failure. This failure method's a little bit unusual. It's unusual for us here, but quite common in South America. This occurs with copper ore, so sized copper ore that has been treated with sulfuric acid. When the pulley is subject to that carryback, the copper ore tends to bond to the ceramic tiles, and it builds up these little pyramids. When the pyramids get big enough, they actually can get torn out, but there's a lot of them that remain in place. And you can imagine with all those little pointy protrusions, what that's actually doing to the conveyor belt.
Definitely.
Not good. Okay, so we'll now move to what we call insufficient service life. So that is, it doesn't require an unplanned stop. These can be treated at a normal planned stop, but what's happening is the lagging's worn out when the mechanical components like the bearings, the locking elements, the shaft are all still completely serviceable. The ideal situation, and what we're always trying to achieve, is to match the lagging to the pulley so that the lagging lasts the full life of the mechanical components. So the only time you're pulling the pulley out is when the bearings have physically reached the end of their service life. That's the goal. Wear is predominantly seen on rubber lagging, which is the photo on the right, the photo in the center. You can see both of these have worn down to the shell. Once you get down to the shell and you start wearing the shell, the consequences are more serious, because if the thickness of the steel shell goes below the engineering design thickness, the pulley has to be scrapped. It can't be refurbished. The photo on the left shows that you can also get wear on ceramic lagging. That's actually one of yours, Peter. That's from Boddington Gold Mine. Edge lifting. So again, this is insufficient service life. It's most common with cold bond pulley lagging, and for pulleys that are operating in a very wet environment. The photo on the left and the photo in the center are both from underground coal mines, and you can see the shell is very, very badly corroded. The photo on the right is also coal bond lagging, but it's actually a pulley that's never gone into service. We'll talk about that a bit more shortly. Similar to edge lifting is what we call joint separation and debonding, which you can see in these photos. If you can imagine every time a pulley goes around, regardless of whether it's a drive pulley or a non-drive pulley, the lagging is subjected to cyclic stresses. Obviously more stress on a drive pulley. Those stresses will always find the weakest point in the lagging. And usually this is the join on cold bond lagging. The joins can open up. Once they open up and moisture is able to get in and contact with the pulley shell, you then get corrosion of the shell, and then the debonding of the lagging continues. Just like with edge lifting, if that corrosion, I've seen pitting where it goes right into the shell. If that pitting reduces the thickness of the steel shell sufficiently, again, you may have to completely replace the pulley if the thickness is below the engineering design thickness. Let's have a look at tile cracking and breakage. This is not an uncommon problem. There are a lot of causes for tiles breaking. Some of them can be completely eliminated, but not all of them. We are going to discuss how to minimize the chances of tile breaking a little bit later on. The last one, or no, the second last one we'll look at is build-up. So this is pulleys typically that are dealing with the carry side of the belt, and excessive build-up can lead to bad belt tracking problems. While you can't necessarily eliminate carryback problems, there are lagging designs that are better at shedding, and so they suffer a lot less from this problem. And we'll talk about those a little bit later on. The next one we're going to look at is on the belt, actually, belt cover wear. So one of the roles of pulley lagging is to protect the conveyor belt. You could argue that that's the most important role of pulley lagging, because the conveyor belt is one of the most expensive components. This particular photo was on a turnover conveyor, and there were very high shear forces on one side of the conveyor, and the non-drive pulleys were wearing out in a band on one side and had to have the lagging replaced every roughly 3 months. So one of the maintenance people decided to put a piece of ceramic lagging where the wear was occurring, and they did fix the lagging. The lagging lasted a lot longer, but the wear was transferred onto the belt bottom cover. This application is, in my opinion, the most difficult application for pulley lagging. These are high tension bend pulleys. High tension bend pulleys fail in a band around the center. You can see here, basically 70% of the lagging is in perfect condition, and that center third has badly failed. You can see also on this pulley, there's a band around the center that has failed. And even on this one here, a direct bond pulley, there's a band around the center. Does anybody know what causes this problem?
No, David.
No. It lines up with the wear on the belt cover. So these pulleys are contacting the carry side of the belt, and this wear profile basically aligns with that wear profile. If we look at it in a graphical form, if you can see this at the top here, this is like a cross section through the conveyor belt. This red line is just to simulate carry cover wear. This little graph across the bottom, the horizontal axis is the face width of the pulley. The vertical axis is the shear force between the belt and the lagging. So out here, out in this part here where the thickness of the belt is uniform, oops, sorry. Out here where the thickness of the belt is uniform, you can see that the shear force is quite uniform. But then when you get to the edge of the wear profile, there's a peak in the shear force, and this then drops down into the center. The reason this happens is that because the belt is thinner in the center, those steel cords are going around a different diameter than the steel cords on the edge. Then when you come over to this side of the wear profile, the shear force comes up again. And then as you move away from the wear profile, it flattens out. This not only impacts the lagging, but also the belt splices. And there's been quite a bit of work done on high tension conveyors where the splices are not lasting the amount of time they should. And these failure points, the areas where they're failing, in a large percentage of the time, they actually line up with these areas of high localized shear stress. So this problem, this issue with the belt cover wear, basically causes a problem with the lagging, and then as both the cover and the lagging wear, the situation gets worse and it damages the belt splices. This is the last failure mode that we'll look at, which is deterioration of spare pulleys during storage. This is predominantly involved with cold bonded lagging. And these examples are for a large export port in Queensland. Most of their pulleys would last 7 to 10 years in service. They carry a spare pulley for every location. So the pulleys sit in the warehouse for 7 to 10 years. Now this site would pull them out to check them before they would install the spare pulley. And in a lot of cases, they were finding the lagging had deteriorated either by opening up at these joins, which means that water can then get down to the steel shell and cause corrosion, or edge lifting. And this particular export coal terminal was spending $2.5 million a year on refurbishing pulleys. Not all of that was lagging, but a significant amount of it was. And that was more than they were spending on the operational pulleys. So I want to have a quick look at the consequences. What happens when lagging fails? So the main consequence of lagging failure is not the cost to replace it. It's actually the cost of the lost downtime, of the lost production time. So if you imagine let's say an iron ore conveyor that's running at 10,000 tons an hour, if they have to do an unplanned stop for 8 hours, that's $80,000 worth of production that they've lost at $100 a ton. So the cost of the lost production is a lot more than the cost of the lagging and replacing the lagging. So how do we avoid lagging failures? At Elastic, we talk about the 4 pillars of lagging performance. And these 4 pillars, you have to have every single one of these has to be correct. If one of them is not correct, the lagging's not going to perform as well as it could. And the 4 pillars are lagging selection, lagging application, lagging design, and lagging quality. Some people consider lagging as a consumable that is, just used up and regularly replaced. We consider it to be an engineered part of the pulley, just like the bearings, locking elements, shaft, etc. And if it's selected properly, applied properly, designed properly, and the quality is correct, with the exception of the high tension bend pulleys, it should last as long as the mechanical components. So that brings the question, how do you choose the best lagging for each application? There's a huge range of laggings, which we'll have a look at in a minute. What is the best lagging? Where can I get information on this? I'll just show you. This is just some of the different types of lagging. If you look here, we've got, just on the ceramic, we've got 1, 2, 3, 4, 5, 6. So there's 7 different types of ceramic, and each one of those has a specific area where it will perform a lot better than one of the other ceramic designs. We'll talk about that in a later course. You've got all different types of rubber lagging, crown lagging, polyurethane, direct bond. So if you were choosing pulley lagging for a pulley, how would you make the selection choice? Or how do you think pulley manufacturers or pulley refurb companies choose their lagging?
It's a spicy meatball. I mean, like manufacturers, they're always leaning towards the cost end of it, with just performing. But then when you're on site and they're trying to solve an issue, that's when they'd be looking at the obviously carry back and the shear force, and then in the case of oil or whatnot, they'd be choosing oil resistant. It's an amazing selection for sure.
No, you're right, James. It's when you're on site, they're looking at, based on, a lot of site people look at past experience. Peter, what do you guys do for selecting lagging?
We talk to you, Dave.
Thanks, Peter. No problems. All right. I asked for that, didn't I?
No, obviously, like James said, James is really correct, and also it depends on definitely depends on the belt design, data, tensions involved, whether it's dirty side or not. We obviously promote or push quite heavy now the hot vulcanizing, as you know. And so a lot of it's also client spec driven.
Yep.
What they want on their dirty side compared to for the non-drives or the drive pulley type. Whether they want direct bond ceramic or rubber back ceramic. For the drive pulleys, it's a discussion with the client.
Yeah, and you're right. There's some clients do have a spec, and that's basically, I guess, this next slide that I'm going to show you is what Peter and James have talked about. So lagging that's on the pulley drawing. So big mining companies have their lagging specified on the drawings. Sometimes it's recommended by the pulley supplier. So that's what you're referring to. I think, Peter, you guys would make a recommendation. A lot of people use past experience. What lagging's been used before. I'm going to show you in a little while a catastrophic failure on a very large conveyor that caused a 3-day unplanned shut, and the lagging was selected based on past experience, and there were various reasons it failed. But the question that was asked in the root cause analysis of that failure was, is there any engineering to support lagging selection? At the time there wasn't, but we are going to talk the next course. We are going to go into detail and look at an engineering tool called Lagging Select for lagging selection. This is actually, these photos are the pulleys that failed on this very high-powered conveyor. You can see here there's two drives, a primary drive which is on the left, secondary drive which is on the right. This was interesting because each one of these drives had a 2.5 megawatt motor, and the lagging had been running for about 5 months with no problems with an ST5600 belt. The mine was going through a tonnage upgrade, and it wasn't a big tonnage upgrade, it was like 10%. And they increased the belt to an ST6300 with slightly thicker covers. So based on past experience, the same lagging was left in place because it had been working okay. Now, when the belt was changed, within 4 weeks, this lagging went from 25 mil thick to 15 mil thick. And you can see here, you can see that the big diamonds have been completely torn away. You can see the extent of the damage. The rubber almost looks like it's melted. So the maintenance people, they had spare pulleys, and the pulleys had the same lagging on. So they put those in, but obviously they were going to fail within 4 weeks. So the question was, what can we put on to solve this problem? So does anybody want to offer a suggestion or a thought? What would you put on as a lagging to solve this problem?
David,
you got... Sorry, James, go on.
Sorry, would you select a lagging that had more ceramic compared to that product?
That was actually one of the first suggestions, and the mine site guys were worried about going to ceramic because this new belt that they put in had a 6-month manufacturing lead time, and it cost $6 million. And they were worried that if they put ceramic on the pulley and the lagging lasted, they may have transferred the wear to the belt.
Fair call.
What happened was we engaged with a company in the States called Conveyor Dynamics, and they did an engineering analysis on this problem. The lagging they came up with, oh, sorry, I should just show you these. These are just some close-ups that have got, you can actually see where the big diamonds have completely been removed, and the small diamonds, you can see they've just bent right over. That all happened in 4 weeks. The lagging that they went to was this herringbone design. It still was hot vulcanized lagging, 25 mil thick, so the same thickness. The herringbone design, there's an engineering analysis that was done that we'll go into in the next course, next month, when we look at the engineering tool. But basically, the aim was to increase the surface area that the power is being transmitted through, and to reduce the flexibility of the lagging so that it wouldn't fatigue as easily. That lagging was installed 2 years ago, and it's getting to the stage where it needs to be replaced. So we've gone from 4 weeks to 2 years. Unfortunately, not unfortunately, the bearings and locking elements are still completely serviceable. We actually need a lagging to last 5 to 7 years. So this is an ongoing project, and we'll talk more about that in the next course. The next pillar of lagging performance is application. Applications extremely important, and in the case of coal bond lagging, where it's put on the conveyor, that can be quite difficult because a lot of times people that are putting coal bond lagging on are dealing with very difficult conditions. You know, they're not in control of the weather. Obviously it's dirty, so it can be very difficult. This is what typically happens when you have an application problem. It's usually seen as debonding from the pulley shell. The photo on the left is coal bond lagging. The photo in the center is direct bond ceramic, where it's been put on with an epoxy. Now, that particular case we think was due to the pulley flexing too much. This one on the right again is coal bond. We'll next look at lagging design. The lagging design includes things like the bonding system that is used for the lagging. It also includes the shape and size of the lagging pattern, the amount of ceramic tile coverage, and also the material that's selected. You know, what sort of flexibility the material has, what sort of coefficient of friction, abrasion resistance, etc. They're all things that go into the design of the lagging. I want to just look at, I want to look at an example of a lagging design that could be improved. So this is a ceramic lagging. It's the one that we looked at before where the tiles have all broken. In these photos, you can see that the ceramic tiles are touching each other. What happens when ceramic's inherently a brittle material. It will crack easily. When you get material carryback caught between the conveyor belt and the surface of the lagging, you get point loads on the ceramic tiles, and because they're touching each other, there's no give, there's no dampening, there's no ability to absorb that shock, and so that contributes greatly to the tiles cracking. We'll look at this in more detail later on, but one of the ways you can reduce the chance of tiles cracking is by putting a layer of rubber in between each of the tiles. Also, if you look at this, when the tiles are actually touching each other, this photo on the left, what that means is that the ceramic tile is only bonded to the rubber on the back. So just in a flat plane on the back, there's no bonding on the sides. So now if you imagine that as the pulley is turning, it contacts the belt and you get a torque or a force applied to it, that force shears on the back of the tile along where the bond line is. And the cyclic nature of this happening every time the pulley turns will find any weakness in the bonding will automatically be found and result in debonding. By contrast, if you look at this pulley on the right, you can see all the tiles are cracked. Like every tile is cracked, even though we have got rubber in between. But I dare to say the cracking is not as bad as if the tiles had been touching. But the big thing that's really important is you can see that the tiles are bonded on the back and around all four sides, and there are no tiles missing. So this additional bonding around the sides is very, very important to keeping the tiles in place when the pulley is operating in really severe conditions. Now, the last pillar that we will look at is lagging quality. So lagging quality, the things that are important is that the person manufacturing or the people manufacturing the lagging must have a really good understanding of how pulley lagging works and what properties are important to getting the best performance. Additionally, you need a good technical knowledge of rubber, ceramic, plastics, metals, and the systems that are required to actually bond them all together. And I guess the last thing is you need a good quality system, which is normal for any production process. I just want to have a look at two examples of poor quality. So the photo on the left and the photo on the right, this is hot vulcanized rubber lagging made from uncured sheet rubber. When they make uncured sheet rubber, it's made in layers or plies. And if you don't get a good bond between the plies, when that type of lagging is on, for example, a drive pulley that's subjected to high shear stresses, the rubber will delaminate. And you can see in the photo on the left and the photo in the center, this lagging has failed because it's delaminated and then it's been torn away by the belt. Photo on the right, again, is an example of poor quality. You can see that the ceramic tiles are missing. And where each of the tiles are, you've just got a nice, neat little pocket. That's a perfect indication that the bonding system has just let go. And you can also see that wherever the belt, like right across this, wherever the belt's been, the tiles are missing. On the edge where the belt hasn't, the tiles are still there. For any of you that are involved in maintenance, I would just like you to think about a couple of these two things. And what would it be like if we could eliminate or reduce maintenance requirements due to lagging failures? So imagine you've got your pulley, you're able to put it on the conveyor. Basically, the lagging operates until the bearings have reached the end of their service life and the pulley needs to be pulled out for a complete refurb. How would that impact people responsible for operations at mine sites? So that's basically it for the course today. Just I'll give you just a quick intro to the course next month. We'll look at the engineering behind pulley lagging and how we basically prevent these failure methods that we've seen, what we can do to prevent them from happening. So we'll cover pulley lagging being an engineered product. We're going to look at an engineering tool called Lagging Select. This is a software tool that is available that can be used to evaluate different types of lagging and look at things like, is there any localized slippage? Am I near the fatigue life of the lagging? How much shear stress does each lagging type induce on the conveyor belt? And it's a useful tool for making decisions about what is going to be the best lagging for protecting the belt and giving you a good service life. We'll look at whether the lagging's operating in a safe zone, the effect of different pulley positions on the conveyor, carry back and build up, operating temperatures, and contact with fluids. Now we've got time for some questions. If anybody's got any questions.
That's very, very good, David. The way you explained all that, it's very logical.
Yeah. Thank you, James. It's easier to explain the way it fails than it is to explain the way you fix it.
Yes, yeah. I mean, in that is the story of how it performs, isn't it? Yeah.
100%. Yeah. So
Yeah.
that's the harder part.
Definitely. Thank you, David.
No worries. Thanks, James. Any questions, anybody? No?
All
right.
good. Thanks very much.
Okay, thank you, everybody, and hope to see you next month.
Yes, definitely. Thank you, David.
See you, James. See you, Dylan. See you, Peter.
Thanks, mate. See ya.